The most important part of this story is happening somewhere almost nobody can see it, hundreds of feet beneath the surface of the Southern Ocean, where swirling underwater eddies as wide as 6 miles across are actively burrowing beneath one of the most consequential pieces of ice on the entire planet. Scientists have now confirmed that Antarctica's Thwaites Glacier, nicknamed the Doomsday Glacier for the scale of sea level rise it could eventually produce, is being undermined by a genuine feedback loop, a self-reinforcing cycle where melting ice actively fuels the exact ocean conditions, capable of melting even more ice, a discovery that reshapes how researchers think about the glacier's most likely future. This is not a slow, simple story of warm water gradually eroding a glacier from below. It is a specific, mechanically understood process that researchers say could intensify as the surrounding climate continues warming, and understanding exactly how it works is the key to understanding why scientists are treating recent developments at Thwaites with such genuine concern. Most coverage of Thwaites Glacier tends to compress an enormously complex, multi-layered scientific story into a single, simple narrative. The ice is melting, sea levels will rise. That narrative is not wrong, but it skips over almost everything that actually makes this specific moment in the glacier's story worth understanding in detail. The specific mechanism driving that melting, why it behaves differently from a simple, steady temperature increase, and why researchers studying it directly are using language like feedback loop, rather than simply describing another incremental step in an already familiar story. Today, we are going to go beneath the surface, literally, and explain the actual oceanographic mechanism driving Thwaites' accelerating retreat, using research most coverage of this story never fully explains. If understanding the real science behind a major climate story, not just the headline version of it, is something you want to keep doing, subscribing means you catch the next breakdown the moment new research comes in. Let's start with the basic setup, because understanding where Thwaites actually sits and what water surrounds it explains everything that follows. Thwaites Glacier sits along the western edge of Antarctica, a massive river of ice roughly the size of Florida, grinding slowly toward the Southern Ocean under its own immense weight. Where the glacier's land-based ice reaches the coastline, a portion extends outward over the ocean as a floating ice shelf, still attached to the glacier behind it, but no longer resting on solid ground. That floating shelf sits directly in contact with ocean water on its underside. And it is precisely that underside, the boundary where solid ice meets liquid seawater, where the most consequential and least visible part of this entire story is actually unfolding. That boundary layer receives far less public attention than the more visible parts of a glacier system, the towering ice cliffs, the dramatic surface crevasses, the calving events where enormous chunks of ice break away and crash into the ocean, all of which make for considerably more compelling video footage than a largely invisible underwater interface. But glaciologists studying ice shelf stability broadly agree that this underside boundary is frequently where the most significant, most consequential changes actually originate, since it is direct contact with ocean water, not surface weather conditions, that ultimately determines how quickly a floating ice shelf like this one loses mass over time. For decades, scientists understood in general terms that warmer ocean water reaching the underside of Antarctic ice shelves could accelerate melting from below. What has changed more recently is the level of detail researchers can now observe about exactly how that underwater melting actually happens, tracked not simply over years, but over individual hours and days, using direct measurements collected from instruments and submersible robots operating directly beneath the ice itself. That finer-grained observation revealed something genuinely surprising. Much of the melting occurring beneath Thwaites is being driven by swirling eddies of water, some measuring up to 6 miles across, that spin and actively burrow their way underneath the ice shelf, rather than simply reflecting a slow, uniform temperature increase spread evenly across the entire underwater boundary. Understanding why an eddy specifically matters more than a general rise in ocean temperature requires understanding what these eddies actually are and how they form. An ocean eddy is a rotating current of water, similar in basic principle to how a whirlpool forms when water drains from a bathtub, except operating on a vastly larger scale and driven by far more complex forces, including temperature and salinity differences between adjacent water masses, the rotation of the Earth itself, and the physical shape of the seafloor and ice above it. When two water masses with different temperatures and salt content meet near an ice shelf, that meeting point can generate exactly this kind of rotating eddy. And because these eddies are actively spinning rather than sitting still, they can physically transport warmer water into direct contact with the ice far more efficiently than a passive, unmoving layer of warm water ever could on its own. That efficiency difference matters enormously for how quickly melting can actually occur in practice. A stationary layer of relatively warm water sitting beneath an ice shelf transfers heat into the ice primarily through slow, passive conduction, a comparatively gradual process limited by how quickly heat can migrate directly from the water into the solid ice above it. An actively rotating eddy instead continuously replaces the water in direct contact with the ice, cycling fresh, warm water into position as the previously warmed layer gets pulled away and mixed elsewhere, dramatically increasing the overall rate of heat transfer compared to a passive, unmoving layer. That mechanical physical circulation is precisely why researchers studying Thwaites found that tracking these individual eddies, rather than simply measuring overall regional water temperature, was essential to actually understanding why melting rates beneath the shelf have been accelerating as quickly as they have. Here is where the actual feedback loop enters the picture, and it is the single most important mechanical detail behind why scientists are describing Thwaites' situation with growing concern. As these eddies deliver warm ocean water into contact with the ice shelf's underside, that contact melts ice directly, producing cold, relatively fresh meltwater that then mixes back into the surrounding ocean. That meltwater does not simply disappear quietly into the broader ocean. It actively mixes with the warmer, saltier water already present in the area, and that mixing process itself generates additional ocean turbulence. That additional turbulence, in turn, helps drive further melting, creating a self-reinforcing cycle where the ice's own meltwater actively contributes to the exact ocean conditions responsible for melting even more ice behind it. Leah Siegelman, an assistant professor at UC San Diego and co-author of research documenting the specific process, described the implication directly. This positive feedback loop could gain intensity in a warming climate, meaning the cycle is not simply a fixed, constant process. It is one capable of accelerating further as broader ocean temperatures continue rising. A feedback loop like this one behaves fundamentally differently from a simple linear cause and effect relationship, and that difference has real consequences for how scientists model the glacier's likely future behavior. In a simple linear relationship, a fixed increase in ocean temperature would be expected to produce a correspondingly fixed, predictable increase in melting, a relationship that would be relatively straightforward to project forward using historical data. A genuine feedback loop instead means that melting itself changes the underlying conditions in ways that promote still more melting, creating the potential for the rate of ice loss to increase disproportionately compared to how much the underlying ocean warming alone would predict. That distinction is precisely why researchers describing this mechanism use language emphasizing intensification rather than simply continuation, since a true feedback loop carries the potential to accelerate beyond what a straightforward extrapolation of current trends would otherwise suggest. This feedback loop connects directly to a second, complementary line of research examining changes across the entire Southern Ocean surrounding Antarctica, not just the specific waters immediately beneath Thwaites. A study published in the journal Science Advances in May of 2026, titled Compound Drivers of Antarctic Sea Ice Loss and Southern Ocean Destratification, documented a fundamental shift in how the ocean around the entire continent is now behaving. Destratification refers to a breakdown in the ocean's normal layered structure, where colder, fresher water typically sits near the surface while warmer, saltier water remains trapped at greater depths, kept largely separate by that natural layering. When that stratification breaks down, warmer deep water that would normally stay isolated from the surface gains a more direct pathway toward ice shelves and sea ice sitting closer to the surface, exactly the kind of large-scale oceanographic shift that would make the specific eddy-driven melting occurring at Thwaites both more frequent and more intense over time. Ocean stratification normally functions as a genuine protective barrier for ice shelves like Thwaites, keeping the warmest available water safely trapped at depth well below where it could ever come into direct contact with floating ice. That layering exists because colder water is generally denser than warmer water, and fresher water is generally less dense than saltier water, creating a natural, stable arrangement where the coldest, freshest water tends to remain near the surface while warmer, saltier water sinks and stays separated below. Breaking down that stable layering removes exactly the barrier that has historically kept deep, warm water away from vulnerable ice shelves, effectively opening a more direct pathway for the kind of warm water eddies described earlier in this video to reach the ice more easily and more often than they otherwise would under normal, properly stratified ocean conditions, confirming that this underwater process is genuinely occurring rather than existing only as a theoretical model, required scientists to develop entirely new methods for directly observing conditions in one of the most physically inaccessible environments on the planet. Researchers have used ice-breaking research vessels to reach the open water near Thwaites' ice shelf and deployed a specialized underwater robot called IceFin, launched directly through boreholes drilled into the ice to swim beneath the shelf itself and gather direct measurements no satellite or surface-based instrument could ever capture. That direct physical observation gave researchers something genuinely rare in climate science, actual visual and sensor, based confirmation of a process that had previously existed mostly as an inference drawn from indirect evidence. a distinction that matters enormously for how much confidence scientists can now place in describing exactly how this mechanism works. Before tools like IceFin became available, scientists studying processes occurring beneath Antarctic ice shelves had to rely primarily on indirect methods, measuring changes in ice shelf thickness from above using satellite radar, or inferring underwater conditions from oceanographic models built using whatever surface and boundary data happened to be available. Those indirect methods produced genuinely useful science, but they left real uncertainty about the specific moment-to-moment mechanics of how melting was actually occurring at any given location and time. Sending an actual robot beneath the ice, equipped with cameras and precise sensors, to directly witness an eddy delivering warm water against the ice surface removes an entire layer of inference from the process, allowing researchers to describe what is happening not as a probable model output, but as something genuinely observed and documented firsthand. That improved understanding of the underwater mechanism connects directly to the more visible changes scientists have documented on the ice shelf's surface as well. Analysis of satellite imagery spanning 2 decades, from 2002 through 2022, found that fractures around a critical structural feature called a shear zone, an area of concentrated stress just upstream of where the shelf anchors against an underwater ridge, have grown substantially, with the total combined length of cracks more than doubling over that period. Robert Larter, a marine geophysicist with the British Antarctic Survey who coordinates the UK side of the International Thwaites Glacier. Collaboration has been direct about what these combined lines of evidence, the surface fracturing and the underwater melting mechanism together, actually mean. The last bit of ice shelf in front of the glacier, he said, is poised to disintegrate, with researchers expecting that breakup to begin as early as this year. Larter's role coordinating the UK side of this joint international research effort places him in a genuinely unique position to synthesize findings across multiple different research teams studying different specific aspects of Thwaites simultaneously, from the underwater eddy and feedback loop research described throughout this video, to the surface fracture analysis, to the broader Southern Ocean destratification study. When a scientist in that specific coordinating role describes the evidence as pointing toward near certain disintegration, that assessment reflects a synthesis across the full body of currently available research, not simply one team's individual findings viewed in isolation from everything else currently being studied about this same glacier. It is worth being genuinely precise here about how these 2 separate lines of evidence, the surface cracking and the underwater feedback loop, actually relate to each other, since understanding that relationship is central to understanding why scientists are treating this moment as significant. The underwater melting mechanism is not simply happening alongside the surface fracturing as a coincidence, it is a primary driver of it. As warm water eddies melt ice from below, they thin the shelf and destabilize the ice from underneath, making the entire structure considerably more vulnerable to the kind of surface stress and fracturing that satellite imagery has been tracking for the past 2 decades. The visible cracks spreading across the surface are, in a genuine sense, the observable symptom of an invisible process unfolding beneath the waterline, which is exactly why researchers studying both phenomena together have reached such a consistent, mutually reinforcing conclusion about where this glacier is actually headed. That relationship between an invisible underwater cause and a visible surface effect is worth appreciating for what it reveals about how genuinely difficult a story like this one is to fully communicate using only the imagery most readily available. A satellite photograph of a crack spreading across an ice shelf is dramatic, easy to understand, and easy to share. Exactly the kind of visual most news coverage naturally gravitates toward. A swirling underwater eddy, invisible to any camera positioned above the surface, delivering warm water against ice hundreds of feet below, is considerably harder to photograph, harder to visualize, and consequently far less likely to actually appear in most coverage of this story, even though it represents the actual underlying cause driving the far more visually compelling cracks that do make it into most headlines and photographs. It is also worth including a piece of more encouraging context here, in the interest of presenting a complete, balanced picture rather than only the most alarming findings available. Separate research examining one particular worst-case scenario associated with Thwaites, involving the catastrophic rapid collapse of towering ice cliffs that would be left exposed once the floating shelf disappears entirely, has recently found that specific extreme scenario now looks somewhat less likely than earlier models had projected. That finding does not contradict or undermine the underwater feedback loop research described throughout this video. The 2 findings concern genuinely different mechanisms, one involving how ocean water melts ice from below, the other involving how exposed ice cliffs might structurally fail once fully exposed above the waterline. The ice cliff scenario specifically concerns what happens after a floating ice shelf like the one currently being melted from below eventually disappears entirely. potentially leaving behind towering, newly exposed vertical walls of ice where the shelf used to buffer the glacier's edge, early theoretical models suggested these cliffs could become tall enough to structurally fail under their own weight in a rapid, self-reinforcing cascade, with each collapse exposing an even taller, even less stable cliff behind it, a mechanism that could theoretically drive extremely fast ice loss once triggered. More detailed research into the actual physics of ice failure has since suggested this specific cascading collapse may not unfold as catastrophically as those earlier models proposed, with natural limits on cliff height and stability likely producing a more gradual failure process instead. Both lines of research, the underwater feedback loop and this more tempered view of ice cliff collapse, are examining real, physically distinct processes, and a complete picture of Thwaites' likely future genuinely needs to account for both. Understanding that distinction matters, since it would be inaccurate to treat every new piece of Thwaites research as uniformly more alarming than the last, when the actual body of evidence includes genuine nuance across different specific mechanisms scientists are studying. None of that more balanced context changes the fundamental picture the underwater feedback loop research has confirmed. Warm water eddies are actively melting Thwaites' ice shelf from below, that melting is generating conditions that fuel further melting in a self-reinforcing cycle. And researchers studying the broader Southern Ocean have documented exactly the kind of large-scale destratification that would make this specific process both more frequent and more intense as the climate continues warming. That is a genuinely different, and in some ways more concerning, kind of finding than a simple observation that ocean temperatures are rising, since a feedback loop, once established, does not require continued external warming alone to keep intensifying. It can partially sustain and accelerate its own progression once set in motion. That self-sustaining quality is precisely what makes this specific research so significant for understanding Thwaites' likely trajectory going forward, even under scenarios where broader global ocean warming might slow or stabilize somewhat in the coming years. A feedback loop that has already been triggered and is actively reinforcing itself does not necessarily require continuously accelerating external warming to keep producing more melting. The internal dynamics of the loop itself, meltwater mixing with ocean water and generating turbulence that drives further melting, can continue operating based largely on conditions already established. That is exactly the kind of mechanism climate scientists watch most closely across many different systems, not just Thwaites, since a genuine feedback loop represents a fundamentally different and generally more difficult to reverse category of change compared to a system that responds in a simple, predictable way to whatever the current external conditions happen to be. If you want to actually follow how this specific mechanism continues to be studied, here is where the most reliable information comes from. The Science Advances study documenting Southern Ocean destratification is available directly through the journal itself, genuine primary research rather than a second-hand summary. The International Thwaites Glacier Collaboration publishes ongoing findings from both the American and British research teams studying the glacier directly, including continued ice fin deployments, specifically designed to keep tracking how this underwater melting process evolves over time. And researchers like Leah Siegelman and Robert Larder, along with their respective institutions, UC San Diego and the British Antarctic Survey, regularly discuss their findings through academic channels and public science communication, genuine primary voices worth following directly rather than relying solely on secondhand coverage. What scientists have confirmed about the water actively churning beneath Thwaites Glacier is a genuinely significant piece of a much larger, still unfolding story, a self-reinforcing feedback loop where melting ice fuels the exact ocean conditions capable of melting even more ice, unfolding within a Southern Ocean that broader research shows is already undergoing a fundamental structural shift. That mechanism, more than any single dramatic photograph of a crack spreading across the ice surface, is really the heart of why researchers are treating this moment at Thwaites with such genuine scientific concern. We will keep tracking this research and the broader Southern Ocean science connected to it, as new findings continue to emerge from the teams actively studying this exact process in the field. If you want those updates the moment they land, subscribing is the way to make sure you do not miss them. And if you want to understand more about how feedback loops like this one work in other parts of the climate system, tell us in the comments what you would want to see explained next. Because mechanisms like this one, invisible, self-reinforcing, and genuinely difficult to fully appreciate from a single photograph or headline, are exactly the kind of science that deserves a closer, more patient explanation than most coverage of a story this dramatic usually has room for. Stay curious, and we will see you in the next one.